So now we have the presentation, isn't it covalent? And once again, we have the quote, sharing is sometimes more demanding than giving, because we wanted to finish up a little bit of what we talked about in terms of covalent bonding. So we need to identify when you can have multiple bonds. You can have more than one bond or share more than two electrons between an element. Um, we'll talk about this a little bit later, but carbon, for example, whenever it bonds with oxygen, is entirely capable of forming two bonds with oxygen if it helps become more stable. We also want to talk a little bit about empirical and molecular formulas. That's actually a review for the summer assignment, but we'll go ahead and go into empirical and molecular formulas again, and we want to be able to use combustion analysis to identify a hydrocarbon based on empirical and molecular formulas. So what do we already know? We know that atoms can share electrons, resulting in a covalent bond. We also know about moles from the last unit. So we want to be able to take these things and the idea of percent composition to figure out what a molecule is, or how much of each atom there is in a molecule. So what we learned in the lab, we learned that electrons can share multiple electrons, that every shared pair of electrons results in a bond. So every shared pair of electrons forms a bond. The covalent bond, we've already shown this, that you have fluorine, that they share these, and so you've got these shared electrons, and we result that as a line, and that line is a bond, or a pair of shared electrons. So that's nothing new. But what may be new is the idea of multiple bonds. The usual suspects for multiple bonds are carbon, nitrogen, and oxygen. They're the ones that you tend to see multiple bonds with. Now, I'm not saying that it can't be something else, but those are the usual suspects that you see. An example of this is if you were to look at carbon and carbon, and hydrogen and hydrogen. Carbons both have 4 valence electrons. Each hydrogen has 1 valence electron. So if you were to look at it, there's a total of 10 valence electrons. For this to be a molecule, all of these atoms have to be connected together. So I can say connect, connect, connect. And what I did is I used 2, 4, 6 electrons, because remember, each one of these electrons represents a bond. What that means is I have 4 electrons left in order to satisfy all of these atoms. Now remember, hydrogen's good. Hydrogen's got 2 and it's happy. Hydrogen's good and it's got 2 and it's happy. But the problem is that each one of these carbons, this carbon thinks it has 4 electrons, 2, 4. This carbon thinks it has 4 electrons, 2, 4. So this carbon right here wants 4 more electrons. This one right here wants 4 more electrons. But the problem is I've only got 4 left. So if I were to give the electrons to this carbon, this one right here is not going to be satisfied. Vice versa, if I give them to this carbon, then this one is not going to be satisfied. So the answer is I need to give the electrons to both. And how I can do that is I can have another shared pair. When I have another shared pair, it gets me closer there. This carbon now thinks it has 6. This carbon thinks it has 6. By adding another double bond, another bond, now I have what's called a triple bond. Now that's the most number of bonds you're going to see is a triple bond. There's not going to be a quadruple bond or anything like that. So you can have 1, 2, or 3 shared pairs. Now here's the process that we go through. We're going to do it for carbon dioxide. The first thing you have to do when you have carbon dioxide is you have to pick a central atom. Generally speaking, you want the central atom to be whatever there's one of. So in this case, it's going to be carbon. Now you count the number of valence electrons you have. This oxygen right here has 6 valence electrons. This has 6 valence electrons, and this has 4. So you see the counts right here. So I have a total of 16 valence electrons that are there. That's to distribute between all of these atoms. So now you have to connect each atom. Whenever you connect each atom in what we call a single covalent bond, you subtract 2 electrons, because remember, each bond is 2 electrons from the total. So I have 2 bonds, that's a total of 4 electrons, I've got 12 left. So now we've got to look to see if we need double bonds or not. I say, okay, oxygen needs 1, 2, 3, 4, 5, 6, and then it would think it has 8. Remember the whole idea of the octet rule. Carbon thinks that it has 1, 2, 3, 4, so it needs 1, 2, 3, 4 more. And this oxygen likewise needs 6. So the problem is that I think I need 16 more electrons. So I need 6 here, 4 here, and 6 here, and that adds up to 16, not 18. And so we can go from here. Oxygen needs 6, and carbon needs 4. So now, if the number of necessary electrons equals the number of available electrons, you just add them. So if these two numbers were the same, and that 18 is still there, if these two numbers are the same, you would just fill it in. You'd say carbon, carbon, and you just fill in the dots as you go. But the problem is that I have what's called an electron deficit. I need 16 and I only have 12. So since I have an electron deficit, I add a double bond. I add another shared pair of electrons and I subtract. So that means instead of having 12 electrons like I did before, now I have 10 electrons. But now, instead of this oxygen needing 6 electrons, it only needs 4. 1, 2, 3, 4. And instead of this carbon needing 4 electrons, it only needs 2. 1, 2. This oxygen still needs 6. 1, 2, 3, 4, 5, 6. So now I need 12 electrons. I need 6 plus 6 is 12. The problem is I only have 10 available because I used 2 of those electrons in forming this bond. So I still have a deficit. So the last step is to form another double bond. When you form another double bond, you realize, hey, this carbon's good. It's got half of each bond, or it's got 2, 4, 6, 8 electrons. And then the oxygens just need 1, 2, 3, 4, 5, 6, 7, 8. And at that point, you need 8, you have 8, you fill them in. And this right here is how you figure out whether or not there's going to be double bonds. It seems like it's a really complicated procedure, but once you actually practice with it, it becomes fairly easy. So, now we get to the example. It says A1. It says determine the number of bonds between the atoms below, and they are shown in order of connectivity. So remember, hydrogen has 1 valence electron, carbon has 4, nitrogen has 5. So I have a total of 10 valence electrons. The first thing that I do is I connect all of them. When I connect them, I've used 4 electrons, 2 here, 2 here. So because of that, I have 6 valence electrons that are left. Now if you were to look at hydrogen, hydrogen's good. Hydrogen's got its 2 electrons, it doesn't care, it's done. But carbon still needs 2 electrons, and nitrogen still needs 6 electrons. So I need 8 electrons. The problem that I have here is that I don't have 8 electrons, I only have 10 electrons. So what I do is I add a double bond. When I add the double bond, now carbon, I got to subtract 2 from my total. Carbon just needs 2 now, and nitrogen just needs 4. But the problem is I only have 4. So I need to do another bond. I add another bond, and whenever I add that next bond, carbon doesn't need any, nitrogen doesn't need any, and if you look, we subtract the next 2, we have 2 valence electrons left, we have 2 electrons, so this right here is our structure. H, C, triple bond, N, and our lone pair. Draw the Lewis dot structure for nitrate, and then it says don't forget the charge. Now remember, nitrate is NO3 minus. And so remember, nitrogen provides 5 electrons, oxygen provides 6 electrons, and there are 3 nitrogens in the nitrate molecule. But then you have this. Remember, that means you have 1 extra electron. That's what the whole idea of the ion has. It's got an extra electron there. So really what I have is I have a total of 24 valence electrons. So the first thing I do is I write my nitrogen and I connect all of my oxygens. When I connect all of my oxygens, I now have 18 valence electrons. Once you have 18 valence electrons, you can say, okay, let me check to see if I can do this. I can put 6 here, 6 here, 6 here, and that'd be good, but I still am missing 2 there. So what I need to do is I need to write a double bond somewhere, and it doesn't matter where you put it. I'll put it right here though. Whenever I do that, I've used 2 more electrons. So now I have 16 electrons left. Nitrogen is now good. It thinks it has 8 electrons. The oxygen needs 2, 1, 2, 3, 4, and then each one of these thinks it needs 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and it matches, so we're good. The next example says explain why the compound CH2 cannot be formed. If you were to look at it, you have carbon and you have hydrogen. Each hydrogen contributes one valence electron, and there are two of them. And then carbon has four valence electrons. So you connect them and you say H, CH, and you would say, okay, I had 6 valence electrons. I used 4 of them. I've got 2 left. So I've got 2 valence electrons. Now, hydrogen is completely satisfied. It doesn't need any more electrons. Hydrogen is completely satisfied. It doesn't need any more electrons. So really the only thing that needs electrons is carbon. So I can put those 2 electrons there. The problem is that carbon is still not satisfied. It still needs another pair of electrons that it needs to get from somewhere. So because of that, the CH2 molecule is not going to form. The thing we need to discuss is the molecular formula. The molecular formula represents the number and types of atoms. An example of a molecular formula is used below. It's C4H10O. Now, one of the things about a molecular formula is it actually doesn't show the connectivity of the molecules. You could have something like this, in which you have the carbons arranged this way and an oxygen out to the side, or you can have it arranged where you have 2 carbons and then an oxygen and then 2 carbons. So the molecular formula does not show the connectivity, it just shows the number of each type of atom that's present. You can contrast that with what we call the empirical formula. The empirical formula represents the lowest whole number ratio between the different types of atoms. Think of it as almost the lowest common denominator. So if you were to look, we have C4H10O2. It's a different molecule than we had last time. You can take all of these things and you can divide them by 2 and you can come up with a whole number, C2H5O. So although this is what the molecule really is, okay, C4H10O2, its empirical formula is C2H5O. So think of the empirical formula as the lowest common denominator. You may be saying, well, why would I want to go from here to here? And that's not the case. You end up going from the empirical formula to the molecular formula. And you can do that by percent composition. So, percent composition. We talked about percent composition earlier this year, but it's the ability to, you can find the percent of mass that's in here, okay, that's due to oxygen. So what you would need to do is you would need to find the total mass of this particular substance, and once you find the total mass of this particular substance, okay, and you see that here, you see we have 4 carbons that are each 12, we have 10 hydrogens that are each 1, and 6 oxygens that are each 16. Multiply it out, these are our totals for each atom. Now we add them up and we get 154. Now to find the percent of anything, it's the part divided by the whole. So the part of the mass that's due to carbon divided by the whole mass times 100. So that's one of the things that's left off here is times 100, because you want to get it into a percent. So for this particular molecule, the C4H10O6, 31% of the mass is due to carbon, 6.49% is due to hydrogen, but the whopping majority of it, 62.34%, is due to oxygen. So this is the percent composition. You should be able to take a molecule, any molecule like CO2, and tell me the percent composition by mass of each element. So I can say, what's the percent mass of carbon in carbon dioxide? Or what's the percent mass of oxygen in carbon dioxide? So now it says the formula shown below to a chemistry student. Determine if the formula could be an empirical formula, a molecular formula, both or neither. Okay, so the first thing we want to do is we want to look and we say, can we divide any of these up? Okay, you cannot divide by 3, because if you divide by 3 you get 2/3 of an oxygen and that won't work. You can't divide by 2, because if you divide by 2 you'd have carbon 1.5 and you can't do that. So this right here represents an empirical formula. An empirical formula is the lowest common denominator. Okay, it's the lowest whole number ratio. Now just because it's an empirical formula does not mean it can't be a molecular formula. So this could also be a molecular formula. And I would have to run some tests to figure out which one it actually is, but in this case the answer would be it's both. It has the possibility to be both. So now it says what is the percent composition of carbon in octane, and then it tells us that octane is C8H18. So the first thing we want to do is we want to write our 2 elements, and we'll write them right here, carbon and hydrogen. Well, carbon has 8 times 12, okay, which ends up being 96. 8 times 12 is 96. Hydrogen ends up having 18 times 1, because the mass of hydrogen is 1, or 18. Whenever you take those and add them together, you get 114. Now you can divide each one by 114, and you can find the percent of each. Now in this particular case, I'm interested in carbon, so I'm going to stick with this top number right here. 96 divided by 114 is roughly 84%. Now, that means that you automatically know what hydrogen is because these two things have to add up to 100%. So that means hydrogen is roughly 16%. This one says thymine is C12H17Cl N4OS, is one of the 4 nucleotides that stores genetic information in deoxyribose nucleic acid. So what is the percent composition of each element in thymine? So this is going to take a little while, but we say C equals 12 times 12, H equals 17 times 1, Cl equals 35.5 times 1, nitrogen is going to equal 4 times 14, and then oxygen is going to be 1 times 16, and sulfur is going to be 1 times 32. Okay, if you're wondering where I got these numbers from, the one number I got from how many of them are there. The second number represents the atomic mass according to the periodic table. So you take these numbers and you multiply them out. So this ends up being 144. This one ends up being 17. This is 35.5. This one is 56, 16, and 32. Whenever you take all those and add them up, you end up with a total of about 300.5. So now that you have 300.5, you can divide each one of these by 300.5 to figure out the percent composition. When you do that, you end up with roughly 48% carbon, about 17% hydrogen, about 35.5, that's not right, it's roughly 10% hydrogen, or 10% chlorine. You end up with 56 divided by 300 is roughly like 18% nitrogen. This ends up being like 5% oxygen and roughly 10% sulfur. Now, this may not add up quite to 100 because I didn't do the calculations and round them to the specific digits, but I went ahead and rounded them individually. So this is a compound that is primarily dominated by carbon because there's so many carbons compared to everything else. So this is burning something to see what it is. Basically what you do is you take a substance, usually it's a hydrocarbon, something that's primarily composed of carbon, hydrogen, and oxygen, and you burn it. And whenever you burn it, it produces carbon dioxide and water. And that carbon dioxide and water can be captured. Water is captured here, carbon dioxide is captured here. Well, you can actually figure out the mass and therefore the number of molecules of each and go back and figure out what the original compound was. So an example of combustion analysis you see here. Combustion analysis, CX plus HY plus OZ leads to these, and then I can use this information to figure out the percent composition. Well, once I use the percent composition, I can now work backwards to figure out what my original compound was. So let's show you how that works. The first step is to convert all the percentages to grams. We're going to assume that there is a 100 gram sample. Because if I assume there's a 100 gram sample, that means this just goes to G, G, and G. Now it's not going to matter because some people say, well, what if you don't have 100 grams? What if you have 0.5 grams or 20 grams? It's not going to matter as far as finding the whole number ratio. It's going to be the same in both cases. Next, you convert grams to moles. You should be familiar with converting grams to moles now, so you're going to take and divide by the molar mass. And when you divide by the molar mass, you get the number of moles of each. Now, you should realize that it can't be carbon 2.5975. That doesn't work because this has to be a whole number. So what you're going to do is you're going to go ahead and divide by the lowest possible number. When you divide by 2.5975, which is the lowest of these three numbers, you get carbon is 1, hydrogen is 2.5 roughly, we'll call it 2.5, and oxygen is roughly 1.5. So at that point, you can now take this molecule, and it still doesn't make any sense because you have carbon 1, H 2.5, O 1.5. So the last thing that you need to do is make these things a whole number. In order to make these things a whole number, you would just multiply all of them by 2. Doing so gives you C2H5O3, which is our molecule that we're interested in looking at. So here is an example. So this right here, if you have C4H10O6, C4H10O6 actually has the exact same percent composition. So if you look, C4H10O6, C2H5O3, they have the same percent composition. So I can't say with any certainty that the molecule is this or the molecule is this. You would need an additional piece of information in order to figure out which one it generally is. So if you were to look, a lot of times what they'll do is they will give you the molar mass at this point. They would say something like this object has a 65 moles per gram, or 65 grams per mole is the molar mass. If it were to do that, you would know, hey, carbon is 24, hydrogen is 5, and oxygen is 48. And if I did my math right, which I didn't, you would see that this ends up being the same number. And it's not 65, that was a bad example. But you have to be able to have some other piece of information to figure out what the molecule actually is. Okay, so the empirical formula is useful because a lot of times you get it in combustion analysis. It is the simplest whole number ratio, but it is not necessarily what the molecule is. Like I said, it gives you the empirical formula, not the molecular formula. You need an additional piece of information, generally molar mass, in order to figure out what the molecule is. So, combustion is just one type of reaction. You can find percent composition regardless of how it's obtained. If you were given percent composition for Na and Cl, you should be able to figure out what the formula is between them. It doesn't matter whether it's combustion or not combustion. So what is necessary for combustion reaction to produce? So what is necessary for a flame to occur? And you should realize that you need some sort of initial energy and you need oxygen. Oxygen is required for any sort of combustion analysis. Okay, next it says a student is attempting to ascertain the identity of a sample based on the information below. And then you have this information, and it wants us to go ahead and say, okay, what is the empirical formula for this particular substance? So remember, we change all these to grams, and we change all these to grams. The next step is to divide by the molar mass. So we divide sodium by 23, we divide hydrogen by 1, we divide phosphorus by 31, and we divide oxygen by 16. When we do that, we get a value of about 1.4. We get a value for hydrogen of 1.4. We get a value of phosphorus of 0.7. And we get a value of oxygen of 2.8. So when we do this, we have to find the lowest one here. Well, the lowest one here is 0.7. When I divide all of them by 0.7, what I end up with is I get, 2 sodiums, 2 hydrogens, 1 phosphorus, and 4 oxygens. So what I can say is that this substance, the empirical formula for this substance is Na2H2PO4. That right there is the empirical substance formula. Now I don't know for sure that that's the molecular formula. It could be something different, but we'll have to take a look at some other piece of information to figure it out. The last example that we have says a sample is combusted, resulting in the data below. Further analysis shows that the sample to have 6 carbons. What is the molecular formula for the sample? So what I do is I start out the same way. These are all grams. Once you divide them by the molar mass, the molar mass is 1, and the molar mass is 16, you get the number of moles. So in this case, it's 3.3. In hydrogen's case, it's 6.67. And in oxygen's case, it's 3.33. When you take these and divide them out. So now you divide by the lowest one, which in our case is 3.3, which gives you 1 carbon, 2 hydrogens, and 1 oxygen. So the empirical formula for this thing is CH2O. Now, it says that you have 6 carbons. Well, here I only have 1. So to have 6 carbons, I need to multiply this whole thing by 6. And in doing so, I get C6H12O6, which is the molecular formula for glucose.